Hi everyone, welcome back to our Littleton Street project. I'm here with David from EcoWise and I'm Anthony from Outlier. Today we're going to just pick up from where we left off last time. Lots happened since we were here.
So yeah, it's progressed along. Now we're nearly completed our framing stage, so let's go inside and check it out.
Hi Outliers, I just wanted to take this opportunity to let you all know that our hybrid home course is now ready and available to purchase via our website. So please head over to outlierstudio.com.au, follow the link via the education to the hybrid home course and check it out. There's also an extensive library of construction details that I hope will bridge the gap to providing a more comfortable, a more healthy and a more energy efficient home, and ultimately a better outcome for all.
So when we were here last, we were talking and we showcased the XPS insulation. It's continuous under the slab. The whole slab's thermally broken from the ground and uncoupled. So now we can see that connection, how it works with the 140mm stud. It overhangs the slab 50mm, and we've got a 50mm XPS insulation here, which is our thermal break. Stops that thermal bridging of the slab transferring heat outside under the bottom plate of the frame. So that's all thermally broken. And yeah, we've got our brick rebate, and then yeah, the XPS insulation continues at the face of that and under the slab. This is our termite barrier. So that goes underneath the bottom plate here. Something very unique about this project is we've got two bottom plates. The first one's gone down just for a bit of easier construction, and that's that termite barrier there just finishes about 50mm short of the inside of the bottom plate, and that's where we've got a nice continuous bead of sealant that's now airtight. And then the wall frames were built whole and then stood up on top of that bottom plate here and fixed to that right through to slab. So that's all nice and firm and secure. From there, like all the joins, they've all been sealed as well to just keep air tightness in mind. We want to stop all that air leakage, so that's all sealed up as well continuously. And then from there, we've got a bit of steelwork in this design and build. It's a nice big cantilever happening up further, which we'll show you shortly. But we've stepped our steel in 50mm as well, so it's flush with the inside face of the stud work. And this allows us to then have a 50mm XPS insulation, the full length continuous of the steel, and that will thermally break all that steel and stop that heat transfer from occurring as well. Again, nice and sealed up around all those connections between the timber frame and the steel work. From there, David, do you want to walk us through some of the unique details of the stud frame?
So generally in Australia, our studs are spaced at 450mm centres, but on this project we're spaced them out at 600mm centres. So the whole purpose of that is the less timber you have in the frame, the more insulation you can install. So we're just trying to build smarter, but it also does have a really good cost benefit because you installing less studs. Generally speaking, a lot of builders will put a block of timber underneath this window trimmer, and that will either go down to there or down to the floor. But once again, to reduce the quantity of timber, we put screws through the sides of this stud back into there, so that window will be well and truly supported. If you can see this up the top here, we've actually turned these jack studs around on their flat. That way we can put in a lot more insulation in there, and just less thermal bridging.
So at the top, you'll also see that just covering our lintel is this strip of external wrap, and David's created what we call a starter strip there. And we're going to go inside and talk more on this in a second to show you what's really unique about this build and how we've got a continuous airtight layer on this external wrap and transferring it inside. But here we've just got that strip of external wrap, and it's taped continuously to a 16mm section of plywood on the top plate or the ribbon plate of the stud frame. And we'll go in there and have a look at that now.
So as Anthony just explained, we have our starter strip of WRB on the outside of this wall frame, and obviously that's going to be a continuous connection from our airtight bottom plate that's down the bottom. Our WRB is going to continue up the outside of our frame into that starter strip, where he explained that we have this piece of 17mm plywood, and that's all been taped and sealed from the outside, and everywhere we've got our joins of the plywood, we're actually sealed up with polyurethane. From there, we're going to have 16mm timber battens, so steel battens in the ceiling here. Our plasterboard will get pushed up hard to this underside of plywood, and a full bead of polyurethane in between that to continue that airtight system.
So the reason that we decided to go with a plasterboard air control layer on this project as opposed to a fabric was just due to cost, and it really allowed us to significantly reduce that and align to the budget on this project. So at this point here, we're 2.7 metres high, and as David just explained, that we're going to have our plasterboard sealed, airtight sealed to this plywood, continuing out to our external weather resistive barrier or external wrap, and it'll come in at 2.7. Then from here, we're actually going to have another ceiling, plastered ceiling at 2.5 metres high or 2.550 high, and that'll allow us to have a cavity between the two layers that we can run all of our services and ductwork, such as our heat recovery ventilation or HRV ductwork, through here without reducing the airtightness of the build.
So as Anthony explained, we have an airtight plaster system here, and that works really well where we have our trusses. But when we have the connection from our double-storey wall frame up here, it can become a little bit challenging. So to overcome that, what we've done is the plywood is airtight up here, and then the connection here is with our steel. We've run our building wrap down this wall, double-storey wall. That will get sealed to a piece of 70mm plywood across the underside of the steel and connect it like that, and that plaster across there is 100% sealed up and airtight. So when we're doing high performance construction, it's very important to know what's in the airtight system and what's out of the airtight system. So here we have our building wrap, which is part of the airtight system, and you can see there's some subfloor out here, which is a balcony that gets cantilevered out. So to ensure we have continuous airtightness, what we should have done on this project is what we did down the other end on the trusses, and wrap the wall first and then put our trusses on, or this end put our joist in. But the way construction is, we've got a bit carried away. There's not actually the end of the world. There's so many different ways that you can get around things. Obviously, it did cost a few extra hours, but that's easily solved. So you can see here we have our building wrap here. We have a structural beam running through here, which we actually use the structural beam as part of an airtight system. We did have to put some wrap around this steel PFC and polyurethane that up. But then once we put our wrap through here to make our beam part of the airtight system, we then put wrap over the top of the beam for water resistance. It's important to make sure you're doing both. You don't want to expose your timber externally. As I just explained before, it's important to know what's outside the airtight system and what's inside the airtight system. So even though we have a wall frame continuing through here, we ensure that we wrap this wall through here first, and that way it's just a continuous airtight system. It was done easy, straightforward, similar to what we did downstairs where we had to detail around all our joists. It just makes it, a nice simple connection and a nice simple detail.
So the continuous air control layer is something that we will talk about extensively throughout this entire build. And this is another perfect example of just keeping that in mind very early on in the design process. So rather than stop our flooring for the upper story at the external frame of here, we've actually continued it right through so that we can connect that and run that continuously down the other side of the outer lower wall. So we'll keep that wrap coming up across the flooring here and then continue up our external walls on the upper section, and that'll keep that air control layer nice and tight and continuous right throughout. So where we're standing, we're actually looking directly north. And that was a really important part of our design, was to ensure that the open plan living where we're standing right now was going to be facing north. In fact, I can feel the sun right now just beaming on us. It's really nice. And to do that, to maximise our solar gain, we wanted to have as much glazing in this space as we could. So where we're standing in this opening is going to be 2 large lift and slide doors. And that's why we have this PFC over the top as well to span that distance, and that will continue out to the cantilever, which we'll show you in a minute. We mentioned earlier as well, that'll all be XPS insulated and thermally broken, as will the steel columns here. And our XPS, no exceptions. In the bottom of the door sills has XPS insulation underneath that as well. Just to give it a little bit more support though, we will put a steel little angle underneath there to support the doors, as it's quite heavy.
And currently it's late September, and you can see the solar gain we're actually getting is through to here. So as that sun rises throughout summer, there's going to be correct shading out here, and we won't get any sun coming into this home. But obviously, you know, at the winter solstice, it's going to be back in here a lot further.
So David touched on the importance of reducing all the thermal bridging earlier, and highlighted some of the details that they've done, again, very unique to this project, to reduce that thermal bridging by reducing the amount of timber in the window support details. And again, that's no exception here. On the external frame junctions and internal frame junctions, they've reduced the amount of timber framing required, and in turn have reduced the amount of thermal bridging that will happen at these locations, because it'll be filled with insulation instead of studs at the how are you thinking that these will, allow plasterboard to continue through or be fixed on lining onto the inside of the frame?
So I'll just jump back one step to the way it's traditionally done. Is that traditionally this stud on a brick veneer wall is moved into this internal corner to pick up plaster. But generally the issue with that is that no one insulates. They put the building wrap on first, and then this cavity where this stud would normally go gets left uninsulated. So we put the external stud out far to the outside of our frame and that obviously, we need something to pick up plaster in here. So we're going to locate noggins in between there on the joins of our plaster sheet, and then noggins in between to make sure it's sufficiently held and we're not going to have cracking with our plaster. And then you see here this piece of timber running through here where this doorway is. With the doors we're using on this project, they do have quite a large sill on the bottom of that. So to reduce the height of them and to make them pretty much a zero threshold doorway, we actually rebated out our concrete slab here. So our doors will be sitting down 38 mil lower than this, than the top of this slab, for a smooth transition across here. This piece of timber is here just as a bit of a protection, just for our construction, that we don't chip this edge out and have a defect with this slab. So one thing that's extremely unique about this project is that we haven't built any internal walls in here. We only built load bearing and external walls. So you can see there's a wall frame coming through here and across there and there, and that's going to be a toilet and ensuite. And I'll explain to you, I'll get Anthony to touch on why that slab is rebated down lower.
So we have a polished concrete floor in this design, and we want to ensure that there's not going to be any tripping hazards at all. So the whole tiled area has been recessed or rebated down, so that when that tile is laid and the concrete floor and the tile marry together and have a flush finish. It's a really nice detail. It certainly aligns with aging in place requirements or desires that people have got in Australia at the moment. And yeah, it's something that again, just aesthetically as well, is really nice to look at too. No steps.
So we have a wall coming through here, and as we mentioned, one thing's really unique about this project is that we haven't built any internal walls yet. And Anthony, can you explain to listeners why we've done that?
So we touched on it earlier as well, but we want to have a continuous plasterboard airtight layer through the entire building. And then we have our lower set ceilings at 2550 below that. And that creates that service cavity that allows us to contain all of our ductwork from the HRV and electrical and plumbing, etc. So what we're going to do is basically create one giant big airtight container out of plasterboard, and then we'll come in and frame up our internal walls. So one of the connections that we just showed earlier was the external connection detail of those frames. But however, when an internal wall does meet an external wall, we need to do something a little bit different as well. And it also helps by thermally breaking, because we're putting insulation in that space where in a traditional sense that probably would have been a stud either side of that internal wall junction and probably left uninsulated. So up at the top here, David.
Yeah, so with traditional construction, they generally, where the internal wall meets the external wall, we have a gang nail, which is just a little plate that has a series of little nails on it, so to speak. But obviously we're putting the plaster in first, so we're unable to do that. So to overcome that, we're going to put in a block up the top there, and obviously the series of blocks, as I spoke about before, in that external corner to pick up plaster. But this one is a structural block. We have screws going through the side of the block, screws going through the plate into this stud. And then when we build this wall frame here, that's going to have an end stud on it. That will have a screw going through the top plate and then into that noggin that we put there. So, you know, we're not, internal walls are structural walls, not probably load bearing, but they are structural as far as bracing. So these internal walls, some internal walls will have braces, but we're definitely over going to come that, you know, the traditional way to do it with our new method here. So, yeah.
Yeah, and there's just one more thing probably to mention to that is that, you know, traditionally internal wall frames are connected to the bottom cords of the trusses. However, we're doing this via using a screw system this time rather than a conventional bracket system that's nailed. And that does mean that we do have two frame inspections in this case rather than the one that would traditionally occur as well. So to ensure that we have a continuous insulation layer, thermal layer in the ceilings, it's really important that you consider how that's going to work when it gets to the external frame junctions where the truss meets that external frame. So we make sure we have a heel height, which is what we have this upstand bit in the back of the truss. It's called the heel or the upstand. Making sure that that height is sufficiently going to fit the thickness of the insulation that we need to have in the ceiling height. So I touched on it earlier about aging in place, and I think in recent studies we're seeing the baby boomers coming to an age where they're starting to retire. We're talking large numbers of people who are probably going to need a little bit of assistance with ambulatory mobility, and one of the things that the clients express to us is by having a second story is how do we get up and down? So we've come up with a system in which this part of the flooring, of the upper flooring can be removed quite easily, and a lift be installed in this corner here to be able to get them up and down. The engineer has just designed a couple of beams quite simply just to tie that off, and then just a couple of little smaller infill joist pieces here that we can just remove when necessary.
So we're explained all the junctions with the airtight system, but in construction there's lots of penetrations that actually go through the plaster. So where we have our power points and light switches on external walls, we're going to use this bracket. So normally with construction they just use a standard steel bracket, but Anthony, with his experience from blower doors and that, there's a lot of air leakage when it comes to power points and light switches. So this is from Tight House, the Energy Efficiency Matrix website. For $5 worth, we have a box here that is fully sealed. We're going to connect that to the plaster with polyurethane, so it's 100% sealed up. The electricians can poke their wires through. We can put more sealant on the inside, and that's going to go internally, but for the sake of the video, let's put it externally on the side of the stud there. And as I said, all sealed up, and we've got an airtight power point and light switch. And to overcome the downlights, Anthony has a solution.
So the power points and external GPOs are all covered with that particular fixture, but yeah, we don't have anything like that available, proprietary available on market. So we've had to invent a little box made out of the same plywood that's used on the top of the top plate, ribbon plate there, and they'll go over the top of the down light and seal, again, just a nice continuous seal of on that of polyurethane on the plywood here to the back side of the plaster sheeting, and the insulation will continue over the top of this, thermally breaking it, and yeah, that'll be keeping an airtight container over the top of every single downlight penetration in the ceiling.
So there's other penetrations that we do have as far as plumbing pipes, electrical wiring, and any like air conditioning or split system pair coil. So that will be 100% sealed up with polyurethane and sealant through the plasterboard to make sure we don't get air leakage.
So one of the other things I'll just note is that internal walls, we don't need to worry about this with this type of system, because we're looking at this giant airtight container approach as opposed to individual airtight wall like spaces with the inside the envelope. And that way, you know, the external walls are all that matter. We just focus on those. One of the things that does also need to be mentioned is that with a plasterboard airtight system, if there is a hole punctured into that plasterboard, then yeah, of course, you know, it creates air leakage at that location. However, it's visible. We can see it and we can repair it and make sure that's the case. And to back that up, the external wrap's also going to be airtight detailed.